All right, section 3.5, we're talking about concavity in the second derivative test. All right, so from section 3.4, we learned about increasing and decreasing functions. All right, but knowing that is not enough to know how to draw a good graph. Okay. For example, right up here, we have two graphs that are both increasing between A and B, but they look totally different. Okay. One goes up like this, one goes up very quickly, and then not so quickly. Okay, this one rises slowly and then rises rapidly. Okay, so both increasing but different. So we need to know something else. All right, and looking up here, we have those two things. Okay, up here we have exactly the same graphs, the first two, except they've drawn some tangent lines on there for you. So notice in this one, all the tangent lines are positive slopes. Same thing on this one. All right, but if you look at those slopes, this one, not quite as positive, this is more positive, and this is more positive. So the slopes are increasing. And this one is very, very steep, so a very positive slope. A little bit less positive, a little bit less positive. So the slopes are actually decreasing. All right, and what that does to the graph is this first graph, we call this concave up. And this second one, we call it concave down.
But it's not going down.
All right, and you probably remember that from the word concave from some science class somewhere. Concave versus convex lenses.
Yes.
Okay, concave looks like a cave. So notice this one is caved. All right, well, the cave part is up. This one we got the cave going, but the cave is down. All right, and here's just examples of, hey, these are decreasing functions on the bottom. All right, but the same thing happens. I'm very, very steep. I'm less steep, and I'm even less steep. All right, but if you think about those values, this slope would be like a -5. This would be like a -1. This would be like a -1/2. So yes, it's becoming less steep, but the derivatives are actually growing. The slopes are increasing. There comes we're getting less negative. Okay, so slopes are increasing still. We have concave up, and here we have the slopes. They're getting more steep. So actually, the derivatives are becoming more negative. So those values are getting less and less. So this is going to be concave down. Okay, slopes are decreasing there as well. All right, so those are the two cases you can have. You got slopes increasing or slopes decreasing. And if you got slopes increasing, you got concave up, slopes decreasing, concave down. I'm giving you examples of when overall the function's increasing or the function is decreasing. All right, so the definition, okay, which we just kind of got through looking at the graph of. A function is differentiable on an interval of a graph of I. Graph of f is concave up if the first derivative, which is the slope, is increasing, and concave down if the first derivative, which again is slope, is decreasing. Okay, so how do you tell whether f prime is increasing or decreasing without actually drawing that graph out? Well, hey, the first derivative tells us what the original function was, increasing or decreasing. So if we take the derivative again and find the second derivative, that tells you where the first derivative is increasing or decreasing. And so that's this theorem down here. It says if the second derivative is greater than 0, then the graph is concave up. If the second derivative is less than 0, the graph of f is concave down. All right, so this is the second derivative. Second derivative gives us concavity. All right, so let's look at this example 1. Determine whether the graph is concave up and concave down. Draw a graph showing all significant features of the graph. All right, so there's our function. That's x cubed. All right, we got 2 as our leading coefficient, so we know the graph is going to overall look like this. Just not sure if we actually have an up and down in the middle or if it's just kind of flattened off. All right, but then if we take the first derivative, which would be 6x squared plus 18x minus 24. All right, we can tell the local mins and maxes like we did last time. We set this equal to 0 and factor. All right, this gives us, let's say, factor out of 6, which leaves us x squared plus 3x minus 4. And if we factor that out, that gives me x plus 4, x minus 1. So our critical numbers are -4 and 1. All right, we do that first derivative test. Yes, I know there's a lot to do. Okay, and you're complaining right now. All right, but you got a -4 for one of your critical numbers and 1 for your other. Okay, you do some test values. So something less than -4, like -5. All right, you can kind of ignore the 6 because it's positive. But -5 plus 4 would give you negative. -5 minus 1 will give you negative. So overall, that's going to be positive, which means I am increasing there. All right, something between -4 and 1, like 0. Plug a 0 in, I get positive and a negative. So I got negative, so it's decreasing. And then after 1, I can plug a 2 in, which will give me positive and positive, so overall positive. So I know it's increasing. All right, so from that, I know I have a local max. All right, at -4. All right, if I plug a -4 back into the original equation, let's see, it's going to give me -128 plus 36, which would give me to, I believe, -92. That's probably wrong. No, that's right, -92. -92 plus 96 would give me 4, and 4 minus 10 is -6 if I did all that correct, which I might not have.
So you're saying you're wrong?
Possibly, except you're not in here. Okay, so I got local max at -4. Okay, which actually I'm pretty wrong. It's actually 100 something. But I'm not going to throw it in a calculator right now. And then local min. All right, local min is going to occur at 1. All right, if I plug that in, probably do that pretty easily. Grab me a calculator. Be 2 plus 9 minus 24 minus 10, which gives me a -23 for my local min. I'll put the -4 in. Let's see. 4 cubed plus 9 times 16 minus 24 times -4 minus 10 gives me actually 102. All right, so those are our local maxes and mins, but now we need to tell concavity. Okay, concavity, we can say, all right, now the double prime of that. So we take this derivative and we find its derivative. All right, so that's going to give me 12x plus 18. Set that equal to 0. Subtract the 18, divide the 12 over. You get -18 over 12. 6 will go into both of those. So our possible place where the concavity changes is -3/2. All right. So if we do a little second derivative test on that, same as the first derivative except with the second derivative. We put our -3/2 on our number line. All right, something less than -3/2, like -2. Something greater than -3/2, like 0. So we plug a -2 into the second derivative. -24 plus 18 will give me negative. All right, so and if I plug a 0 and I get positive 18, so it's positive. So what that tells us based on that previous theorem is between the -infinity and -3/2, I'm concave down. between -3/2 and infinity I am concave up. All right, so what does this tell us all about our graph? All right, sure would be nice if we could factor the original. We could go back and find P's and Q's like we did in Advanced Math Plus to figure out where it crosses the x-axis. But, which we'll probably do that later in a different lesson. All right, but we know we have a local max at -4 and 102. So somewhere right there. And then at 1, -23, I've got a local min. So somewhere about right there. And then at -3/2, I know I'm changing from concave up to concave down. So -3/2 is right about here. You can plug it back into the original to figure out exactly what that value is. And so I know those 3 points. Okay? I know at the very beginning, coming down from the bottom, all right, I'm concave down until there. And after that, I know my graph is going to start to curve like this. It'll be concave up with that minimum down there, which I didn't draw very well. So up, concave down until then, concave up, and there. All right, and that's example 1. All right, if you plug it in your calculator, you're going to have to change your window values to go from like -50 to 125 or so on the Y's so you can see everything. All right, now if you notice, at this point right here, at -3/2 and whatever that Y value is there, it changed from concave down to concave up. All right, we actually give that a certain name. Okay, we call that an inflection point. All right, or point of inflection. Okay, if the function changes from concave down to concave up, or concave up to concave down, at that point it's called a point of inflection. All right, and inflection points always occur at a C value when the second derivative is equal to 0. Okay, it's kind of like a critical number of the second derivative. The book doesn't call it critical numbers of second derivative. I kind of like that little nickname there. Okay, so wherever the second derivative is undefined or 0, an inflection point is going to occur there. All right, but just like Fermat's theorem with local mins and local maxes and critical numbers, all right, not every place where the second derivative is 0 undefined corresponds to an inflection point. Okay, and not just because it makes the original function undefined, it could be something else going on. Okay, so inflection points occur when the second derivative is 0 undefined. But just because the second derivative is 0 undefined, it doesn't, in fact, mean there's an inflection point. Okay, if you remember back to your ACT in September, that's kind of like your Chicago and Illinois question. Okay, if you live in Chicago, you live in Illinois. But if you live in Illinois, it doesn't necessarily mean you live in Chicago. Okay, now you all had questions on that one. So same type thing here. If you are an inflection point, your second derivative is 0 undefined. But if your second derivative is 0 undefined, doesn't necessarily mean you're an inflection point. All right, so let's look at this one. Determine where the graph of x to the 4th minus 6x squared plus 1 is concave up and concave down. Find any inflection points and draw a graph showing all significant figures. So, first thing we do is take the first derivative, which would be 4x cubed minus 12x. All right, to find significant features, that's our mins and maxes, so let's find those. Set this equal to 0. All right, which will give me, factor out a 4 and an x, that leaves me with x squared minus 3. All right, so the 4x is 0 and x is 0. All right, if you add the 3 and take the square root, this is going to give you a square root of 3 and a negative square root of 3 as my critical numbers. right, do a little first derivative test on it. All right, we got a negative square root of 3, a 0, and a square root of 3. We pick some test values. Something less than a negative square root of 3. Square root of 3 is somewhere between 1 and 2. So let's plug in a negative 3 over there. We know that's definitely smaller. Plug a negative 3 in. Outside would give you negative. Inside would be a 9 minus 3, which would give you a positive 6. So overall, you're negative. So I'm going down. Something between negative 3 and 0, like negative 1. You'd have a negative on the outside. A 1 minus 3, so negative on the inside, so positive. So I'm going up. If I plug a 1 in, the outside will be positive, inside will be negative, so negative overall. So it's going down. If I plug a 3 in, outside would be positive, parentheses would be positive as well. So positive overall, so it is going up. So that tells us a lot of things. That tells us I've got a local min here. It's square root of 3. And another minimum at the positive square root of 3. And a max, or local max, at 0. All right, if I plug those values in, all right, 0 is going to be 1. All right, and square root of 3 and negative square root of 3 are going to give you exactly the same thing. Let's plug that in. Let's see, square root of 3 raised to the 4th power minus 18 plus 1 will give me a negative 8. Okay, so this happens, a negative square root of 3, negative 8 is a min, 0, 1 is a max, and square root of 3, positive 8 is a min. All right, so those are our relative mins and maxes. Now we can find concavity. Concavity. Don't have to go to the dentist to get that filled. Just the calculus class. So second derivative, take the derivative again. That gives me 12x squared minus 12, I believe. Set it equal to 0 and factor. That gives me x squared minus 1, which that factors into x plus 1, x minus 1. So your possible points of inflection, okay, are going to be when x is negative 1 and positive 1. So I'll stick that on my number line for my second derivative test. Negative 1, positive 1. This is my double prime. And plug in test values into the second derivative. All right, if I plug a negative 2 in, kind of ignore the 12, it's positive. Plug a negative 2 in there, it's going to give me a negative and a negative. So that's going to give me positive overall, so we know we are concave up. All right, in between negative 1 and 1, I can plug a 0 in, which will give me positive times a negative, which is negative. So we got concave down. And then something after 1, like 2, will give me positive and positive. So that's positive, so I know I'm concave up. And if you plug those points of inflection, my POIs, I'll plug a negative 1 in, that's going to give me 1 minus 6, which will be negative 5. Negative 5 plus 1 will give me negative 4. So f of negative 1 is negative 4, and f of 1 would also be negative 4. Okay, just like with the relative maxes and mins, to find those actual points, you got to plug it back into the original function. All right, so let's see. I got negative square root of 3. All right, which if I plug that in just to figure out the decimal value on that, if I don't remember it, square root of 3 is about 1.73. So a negative 1.73, so somewhere around there, I'm down at a negative 8. All right, let's see, that's 7. So somewhere right there. And then at 1.73 over here, so somewhere about there, I'm also down at a negative 8. At 0, I'm up at 1. All right, so those are my maxes and mins. And then at negative 1, negative 4. So let's see, right about there. And at positive 1, negative 4, those are where my concavity changes. Those are my points of inflection. All right, and we could solve this one right here for 0, the original function, to figure out the x-intercepts. It's going to take you a little quadratic formula and then setting it equal to x squared. So we won't do that right now, but we know that it's concave until I get to there, concave down from here to here, and concave up after that. All right, it is going to be symmetric because this is an even function. Example 2. All right, now you could have no inflection points, like this one right here. X to the 4th. We should all know what x to the 4th looks like. All right, it's just a little flatter parabola. Okay, but if I take the first derivative, that gives me 4x cubed. Okay, so that means that my critical number, when I set that equal to 0, is 0. On either side of 0, a negative 1 will make it negative, so it's going down. And a positive 1 will make it positive, so it's going up. All right, and then if I do the second derivative, that gives me what? 12x squared. So again, my point of interest for a point of inflection would be 0. All right, and if I plug a negative 1 in, that's going to give me positive, so concave up. If I plug a positive 1 in, that also gives me positive, which is going to be concave up. So concavity does not change. Okay, it's concave up both places. All right, and just so happened on this one that 0 was actually a minimum value. All right, so we know that the whole graph is going to be concave up, just like x to the 4th always looked. All right, now, on those past couple examples, we did the first derivative test, figured out the extrema, and we did the second derivative test to find out the concavity. Okay, you can actually just do the second derivative test in a lot of cases. All right, because what's going to happen if you got something concave down, all right, and you have a critical number where the function's equal to, or the derivative is equal to 0, that means you have a 0 slope. Well, if you're concave down and you got a 0 slope, that's going to be a maximum. All right, and if you're concave up and have a 0 slope, it's going to be a minimum. Okay, and if you think about it, it makes sense. Even though it kind of sounds a little bit backwards, concave down, you're going to have a maximum, concave up, you're going to have a minimum. You can kind of see how those are opposites. But if you think about the graph, if it's going down, that maximum or minimum is going to be at the top, so it's a max. And if you have concave up, that critical number is going to be a minimum because that's going to be at the base of it. All right, and that's the second derivative test. All right, if the second derivative is less than 0, all right, and the derivative of c is 0, then it's a local max. All right, if the derivative of c is 0, and the second derivative is greater than 0, meaning it's concave up, then that function point right there is going to be a minimum. So it's going to save us a little bit of time, not a whole lot, but a little bit of time. So let's look at example 4 to find the local extrema. All right, so on this one we just have to do, still have to do first and second derivative. So first derivative would be 4x cubed minus 16x. 4x cubed minus 16x. All right, we do have to stop here and find the critical numbers. So if you factor out a 4 and an x, that'll leave you with x squared minus 4. So your critical numbers are 0, 2, and negative 2. All right, but you don't have to stop here and do the first derivative test, because we can go straight to the second derivative. We find the second derivative. That is going to give you 12x squared minus 16. Yep, if you factor out, let's see, what, a 4, that's going to give you 3x squared minus 4. If you add the 4, divide by 3, and take the square root, then your possible points of inflection, a little star because they're possible, are going to be at the square root of 4/3 and a negative square root of 4/3. All right, if you want to clean that up again a little bit, turns out to be that's going to be 2 square roots of 3 over 3, a positive or negative. All right, so if I do the second derivative test, all right, we got a negative 2 square roots of 3 over 3. We got a positive 2 square roots of 3 over 3. All right, so we think about it. 4/3, it's a little bit bigger than 1. The square root of it's going to be still a little bit bigger than 1. So if I do my test values, let's plug in like a negative 2 to be safe, a 0, and a 2. If I plug that into the second derivative, all right, if I plug a negative 2 in, that's going to give me 12 minus 4, which is positive. All right, so it should be concave up in the first section. All right, at 0, it's going to give me a negative in the middle, so it's going to be concave down. If I plug a 2 in, 12 minus 4, which is 8, which is going to be positive, so concave up. All right, so what does that tell us about our extremum? All right, well, where are 0 and 2 and negative 2? All right, 0 is right here in the middle. All right, so we have concave down and a critical number. So concave down and a critical number from the first derivative tells me I'm going to have a local max at 0, which ends up being 0, 10 if you plug it in. All right, now I have a local mins at negative 2 and positive 2, because those are in those universes, those intervals, where the graph is concave up. And so if you have a critical number where it's concave up, that's going to be a min. So those mins are going to be at negative 2, which would give me, let's see, plug a negative 2 in, it'll give me 16 minus 30, negative 16 plus 10, which is negative 6, and 2 negative 6 will give you exactly the same thing. All right, so you could start, when you're doing all this and putting it together and graphing, you save yourself a fraction amount of time by not having to do the first derivative test. All right, little note here. If the second derivative is 0 or undefined at a point where your critical number is, okay, so if you have your critical number and the second derivative of that critical number is 0 or undefined, then it doesn't tell you there's not a local min or maximum there, okay? We don't know. Okay, it could be local min, could be local max, could be neither. The second derivative test kind of fails there, and so we have to go back and do the first derivative test. Okay, so just because it's 0 in the second derivative doesn't tell you anything, it tells you you have to go back and do the first derivative test, unfortunately. All right, so let's take an example of this. Let's look at, got a couple problems here. A, is f of x is equal to x cubed. So the first derivative would be 3x squared. So our critical number would be 0. And the second derivative is 6x, which what makes that 0? A possible point of inflection is also 0. All right, so we had a case where, hey, the critical number was also a possible point of inflection. Okay, so we can't tell from the second derivative test because we don't know if it's concave up or concave down there. It actually changes concavity right there. So we have to go back and do the first derivative test. Plug our 0 in, plug in our test values back and do the first derivative. All right, and if you're negative 1 in there, that will give me a increasing, because that will give you 3. If you plug a positive 1 in, it also give you 3, so it's increasing. So it turns out that that's not a local min or max. Okay? In fact, if you remember what x cubed looked like, looks like that. Okay, so it's not a max or min, but you can tell it's doing what? Concave down and then concave up. Right? It's not always going to happen like that. Okay? Our example we did earlier with f of x is equal to x to the 4th. All right, its first derivative is 4x cubed, so critical number at 0. And the second derivative is 12x squared, and so your possible point of inflection is also 0. Okay? And these numbers don't have to be 0, but the fact that they're a critical number and a possible point of inflection tells me that the first derivative and the second derivative are both 0 there. So this doesn't tell us anything. So we have to go back and do the first derivative test again, figure it out. Plug a negative 1 into 1 here on this one. We'll get a negative to the left, so down, and a positive to the right, so it's going up. And so we actually have a local minimum there. Okay? If you think about that graph, that looks like this, which we've already drawn. Okay? And then for C, the same thing, except the function's what? Negative x to the 4th? So the same thing is going to happen, except my graph is going to look like this. All right, and so if you did the first derivative, I'll probably have, let's call those g's, sorry. First derivative would be a negative 4x cubed. Second derivative would be negative 12x squared. So my first derivative test, or second derivative test would fail because 0 is for both of them. And first derivative test would tell me, hey, this is going to be positive, so up, negative, so down, so there is actually a maximum right there. Okay, so 3 different times where the second derivative test is inconclusive, it fails. All right, and we'll save these last 2 examples for either another video if it pops up or for class next time.